Okay, so please take it over, Dustin.
Okay, thanks. Nice to see everyone again. I was supposed to be talking about, I turn it vertically. I guess I can, yeah. Let's see. Okay, so I was supposed to be talking about Morava E theory today, and I will, but I feel like there's not really 2 hours worth of material there. So I'm gonna actually make a few, to continue a little bit the story Peter started with in the morning. It looks like my camera's frozen, right?
Yes.
Yes.
Huh. But that's not really so essential. I guess what matters is whether you can see what I'm writing, eh? Maybe it'll unfreeze by itself at some point. Let me, okay, anyway. So I want to recall a theorem of Seusslands. Which is a statement about K theory of the complex numbers that, well, of course, the statement doesn't have anything to do with condensed math a priori. But so it says well, there's two different kinds of K theory of the complex. Well, there's classically two different kinds of K theory of the complex numbers. There's the usual algebraic K theory of the discrete ring C. And then there's the, well, K theory of the category, okay. There's the little ku, which is the group completion of the category enriched in anima. In the anima, BGLNC. So as you take the category of finite dimensional complex vector spaces and isomorphisms between them, that's a topological category with the usual topology on GLN, but then you pass to anima instead. And then you get an infinity category, and then you group complete that. That's one way to define this so-called connective topological K theory spectrum. And it's homotopic groups, are the usual thing about periodicity. So it's Z if n is even, and 0 if n is odd. Whereas this is kind of, at least a priori, quite mysterious. Because, algebraic K theory of discrete rings is a little strange. But anyway, Seusslands' theorem says that this map is an equivalence, is an isomorphism with finite coefficients. So in other words, if you take, these are two spectra, there's this, if you take this modulo n, it's the same thing as ku modulo n. So it's z mod n when n is even and 0 when n is odd. So this spectrum mod n is the, so I'll just recall that for a spectrum, there's always a multiplication by n map, and this x mod n is the cone of multiplication by n. So it's the thing that fits in a distinguished triangle. So on homotopic groups, there's a long exact sequence relating the homotopic groups of the mod n reduction of x and the multiplication by n maps on the homotopic groups of x. Right. So this says, so you have this algebraic K theory, which is mysterious in general, but this is saying with finite coefficients, it turns into topological K theory kind of magically. So it looks like my camera is not indeed, wow, I just had to threaten it and then it popped back into life. Okay. So I want to show how this is a corollary, how this is a corollary of the theorem Peter just discussed about the about the solidification of the condensed K theory of C. So these were classical objects, the algebraic K theory of the discrete ring and the so-called topological K theory. It's probably better to call it animated, I guess. In terms of this distinction between topological phenomena and animated phenomena, this is really an animated. It's built from the anima, not the topological spaces themselves. But you can take the analogous thing built from the topological spaces GLN and then BGLN in the world of condensed anima. And then we have this is a full condensed spectrum. And it determines both of these things. It determines K of C discrete, and it determines the other one. The one thing, which is just a consequence of the definition, if you take the underlying spectrum, so you evaluate on a point, you do get the K theory of C as a discrete ring. So the underlying spectrum is the usual algebraic K theory, but then we saw that the solidification of this condensed spectrum is also a usual spectrum. So it's a pure anima, so to speak, and it is this little Ku. You could also use for the purposes of this argument, you don't have to use solidification. You could also use this homotopy operation, which Peter also discussed. So you can also ask for the initial pure spectrum, not condensed spectrum, but honest spectrum with a map from K of C, and it will also be Ku, and the argument is very similar. And there you don't even need to know anything about solidification. So it's a condensed spectrum whose underlying spectrum is the usual algebraic K theory, but there's this operation you can perform to it which recovers topological K theory, kind of passing to the homotopy type or taking the anima of it, which can also be modeled by solidification in this context. Okay. So then the more refined version of Seusslands' theorem is that this, if you take this condensed spectrum K of C mod n for any n, it's always discrete. So it is an ordinary spectrum and not a condensed spectrum. So why does this imply Seusslands' theorem? Well, if K of C mod, this implies that K of C mod, you can always take the underlying spectrum, view it again as a condensed spectrum, and then it'll always map by some universal property to K of C, just like a topological space with discrete topology always maps to a topological space with ordinary topology. So you always have a natural map like this, and the fact that this is discrete, and this map is a natural transformation of exact functors, so it commutes with modding out by n. So an equivalent way of saying this is that when you look mod n, K of C is discrete, but then also K of C mapping to, say, the solidification of K of C. So we can take this mod n. Well, what am I trying to say? Let me erase and try to write this a different way instead. Okay. So, but now this is in particular discrete. So that oops, now I need to go back to something that can draw. So any discrete thing is its own solidification, because solidification is solidification sends the point to the point, so to speak, and commutes with colimits. So anything discrete is already solid, therefore its own solidification. But solidification is also an exact functor. It commutes with all colimits. So this is the same thing as Kc mod n, and that was the same thing as Ku mod n. Right. So if you know this condensed spectrum mod n is discrete, then on the one hand, it has to be the algebraic K theory mod n, but on the other hand, then the solidification doesn't do anything to it mod n, so it must also be the topological K theory mod n. So that's why this is a refinement of Seusslands' theorem. So now let's give a proof. So first let me give a little lemma, which is that how do you tell whether a condensed spectrum is discrete? So or even I could say anima too. I mean, if and only if we're all extremely disconnected.
The bottom up or?
Sorry? Was someone asking a question? I didn't quite come through. No, okay. So a condensed anima is discrete if and only if we're all extremely disconnected S, and all points, like actual points of that topological space, the colimit over all open neighborhoods at that point, let's say closed and open neighborhoods if you like, of x of u, mapping to x of little s. So that's x of a point, is an iso. So, well, what's the proof? So if you look at the formula for the condensed spectrum associated to a discrete spectrum, so say if A is an ordinary spectrum, then the associated discrete condensed spectrum, let's call it A discrete, is defined by A discrete of S should be the sheafification. It's the global sections of constant sheaf. With value A on the topological space S. Because on any profinite set, there's the closed and open subsets form a neighborhood basis for the topology. And then the sheaf condition is just the condition of finite disjoint unions. So it's the same as the topology that's describing what a condensed anima is. So this means that a condensed anima is discrete if and only if U maps to X of U is a sheaf, is a constant sheaf for open subsets. U maps to S for S extremely disconnected. And these extremely disconnected spaces are zero dimensional, and therefore you can test and then we have an a priori map, right, from the discrete guy with the same underlying spectrum to our guy. And we want to test that then we have an isomorphism on global sections. Then it's enough to test it on stalks because these are zero dimensional spaces. And then it becomes exactly this condition here. This is, can check isomorphism on stalks. Right. So that's this criterion here. So now let's apply it in the case of K theory of the complex numbers. So then we can look at both sides. So we have the filtered colimit over all U containing S of, well, X of U, but X of U is by definition, so if we take this to be closed and open. So these sets are totally disconnected. They have a basis for the topology consisting of closed and open subsets, which will themselves then also be extremely disconnected. And we've specified the value of our condensed K theory on extremely disconnected spaces. So this is the K theory of continuous functions from U to the complex numbers. So we take this ring of continuous functions, right, and then modulo n. And this is the same thing as we can pass filtered colimits through algebraic K theory of rings. So that's the same thing as the K theory of the ring of germs of continuous functions from a neighborhood of modulo n. Now note, this ring of germs of continuous functions is an example of what's called a Henselian local ring. With residue field C via evaluation at the base point. So this is some form of a implicit function theorem for continuous functions. So like, this is some version of implicit function theorem or inverse function theorem. Yeah. So, or basically, if you have this comes down to the fact that if you have a tall map of complex varieties, then on topological points, it's a local homeomorphism. On complex points, it's a local homeomorphism. That's kind of equivalent to this statement here. And then Seusslands' rigidity theorem for Henselian pairs for Ancelian local rings gives what we want. So ISO for all such R and maximal ideal M. Right. So, well, I said this gives a new proof of Seusslands theorem, but that's not quite correct because the main point in Seusslands argument, the main point in Seusslands paper was to verify this rigidity property, which is the real crucial input. And they're going from there to his theorem connecting algebraic K theory and topological K theory is just a matter of organizing the arguments in a correct way. But what this shows is that kind of this framework of condensed spectra gives a good way of organizing the arguments. So you don't have to be clever like Seussland was to deduce one from the other with this framework. You just follow your nose. Whereas if you look at what Seussland did, you realize he had to be a little bit clever to make that deduction. Okay.
There was a question in the chat that I think you know more about than I do.
What's that? Which one?
Do you see this? This is a semi-topological K theory.
Oh, semi-topological K theory. Yeah. Semi-topological K theory. Semi-topological K theory. I used to know about this. This is embarrassing.
I think it's a thing where you plug in C algebras and but somehow remember the topology or regard somehow all the automorphism groups as anima or more or less.
Yeah, but what kind of object is it in the end?
Somebody else must answer this. But I think you want to explain to me how this works.
Yeah, I know. I used to know it. I really did. I simply can't remember anymore. I forget what kind of object it's supposed to be at the end of the day. Yeah,
just a spectrum?
Is it just a spectrum?
Yes.
Uh-huh. Wait. Yes, now I remember what it is. Okay, thank you. Yeah, it's just this, yeah, this thing with KU, just for a more general C algebra instead. That's all it is. Yeah, so it's just the analog of little KU for a general, say, finite type algebra over the complex numbers. So you take the algebraic, yeah. But for other algebras, it's not, for the case of the complex numbers, this is just easy to calculate. It is just topological K theory. But in general, the relation between semi-topological K theory and the topological K theory of the C-valued points is more intricate. So it kind of behaves kind of halfway between algebraic K theory and topological K theory of the topological space given by the C-valued points. But yeah, in terms of the definition, it's basically just the analog of this for more general C algebras.
And so it's also, again, the solidification of the K theory as a condensed.
Yeah, probably it is, yeah. But given that I just forgot the definition, maybe don't take that as gospel. But it really feels like it should be. Yeah, I think that's right. Yeah, so I'll write probably for A C algebra, the condensed K theory of A solidified is the same thing as the semi-topological K theory of A, and it should also be the same thing as the homotopy type of the condensed K theory, so to speak. Yeah. Okay. Right. Yeah, I also want to mention actually this result that I said this refined version of Seusslands theorem that K theory of C mod n is discrete is actually applies much more generally. So same argument works. If you take that shows that K of A mod n is discrete for any say Banach ring A in characteristic 0. Or if you yeah, this characteristic 0 assumption is not too also in characteristic P it often works, but I won't get into the details of that.
But you just have to assume it's not characteristic dividing n. N must be invertible.
But even if it is dividing N, it's often true in characteristic P as well.
But in particular, if N is invertible in A, it's definitely true.
Yeah, if N is invertible, or if N is invertible in A. Yeah. But even, yeah, it's quite, as long as the topology, if the topology is pure p-adic, then also it doesn't matter what character. Yeah, it does. Yeah. Anyway. Yeah. All right. So for example, you could also take A to be QP or something like this. And for also for A equals QP, you can you might wonder what the solidification of something like this is, and this can also be described. So so let me recall the localization sequence. So we have K of ZP goes to K of QP, and then there's a fiber term. Maybe I'll make it a cofiber term, and then suspension of K theory of FP. And now this works just in the same way as condensed spectra. So, but this term here is discrete, because if you look at the condensed K theory of a discrete ring, it's already a discrete spectrum. So, yeah, you can just see that there. If you have a discrete ring, then the ring of continuous functions from a profinite set to it is the filtered colimit of the rings of continuous functions from the finite quotients of that set, and then that passes to K theory, and that shows you that it verifies the criterion that you have to check that a condensed spectrum is discrete. But these two are non-discrete. But that means that to understand the solidification of the K theory of QP, it's enough to understand the solidification of the K theory of ZP, because the fiber term is discrete. And then for the K theory of ZP, the nice thing is that this, you can sort of pull in the inverse limit. And these are all discrete again. So you can prove this in basically the same way as Peter sketched for the complex numbers. So you reduce to understanding what the solidification of BGLN is, but then that's just the bar construction on the profinite set GLN, and you know what solidification does to, S bracket a profinite set. Sort of by construction, it sends it to the inverse limit of over the finite quotients, and then you have to be a little careful with organizing the argument in the correct way, but you end up with this. And I didn't, but I should say that maybe addressing the question in comment. In general, this solidification operation.
By the way, I mean, can't you not prove that K of CP? Can you not directly prove that this is pseudo-coherent?
Yeah, it's pseudo-coherent too, that's right, yeah.
And then we would only have to check the maps against the integers, which is maybe easier.
Then we'd have to check what, sorry? Yeah,
I'm not sure.
I'm not so sure it's easier, because how do you control maps out of the right-hand side, right?
Yeah, okay.
Yeah, I mean, it is profinite in each degree, the right-hand side, so a priori, right. But yeah, what is the general background to these kinds of investigations? Or should I start talking about Morava E theory and then come back to K theory? Maybe I'll say the background to these kinds of questions is that if you take like K theory of complex numbers, or K theory of the p-adic complex numbers, or K theory of QP or something, these are big and unreasonable. In the same way as things like QP tensor Z QP are. For example, if you look at K2 of a field, this is F cross tensor over Z F cross modulo some relation, the Steinberg relation. And in particular, you're seeing this algebraic tensor product up here. And even if you go ahead and consider everything as a condensed thing, it's not going to really help you out because you have this really weird group on the right-hand side that doesn't look very nice. But they all have, but they all map to nice things, to nice targets. E.g., with finite, if you take finite coefficients, as we just saw, then it's related to topological K theory or this inverse limit of things, which is indeed profinite. So in each degree, you have something finite here. So you map to something nice, a reasonable topological abelian group, basically. Or for the K theory of complex numbers, they're regulator maps, regulator maps. Well, or at least in the K theory of the real numbers. So the K theory of 4n plus 1 of R maps to the real numbers. So you have these a priori crazy groups given by the algebraic K groups of these fields, but there's a way to map, there's always ways to map them to nice reasonable things. And you'd like to know what the initial reasonable thing is that K theory of R maps to. So this is very much related to algebraic cycles are kind of unreasonable as an abstract abelian group, but you map them to various Weil cohomology theories, for example, which are reasonable. And then these Weil cohomologies might have different relations between them given by comparison isomorphisms, and you want to kind of conglomerate that and see what the see what you get, the best possible approximation to algebraic cycles that still is a reasonable topological abelian group or something like that, say. There's there exist good guesses. There exists a good guess for, say, the reasonable K theory of the complex numbers. Basically, it should be gotten by amalgamating what you see in the topological K theory, or the anima K theory, little ku, and what you see as coming from regulator maps. And what you end up seeing is you should have a z in degree 0. So, you should have a z in degree 0. In degree 1, you have c cross. That's already a reasonable. That's the K1 of a field is always the units in the field. So you have c cross. But maybe it's best to uniformize that and write that as c modulo 2 pi I z for the purposes of what's going to come later. And then you should have 0 here, and then you should have c mod 2 pi I squared z, and then 0, and then so on. Right. So this would be a candidate for what would be like the completion of the what we would like to view as the completion of the condensed K theory of C. We expect this to contain all of the reasonable information. And so how would you so what's happening with solidification in terms of this this picture here? Well, if you were to go and solidify this description for this reasonable K of C, then you would find you would indeed just get little ku, because you have a z in degree 0. You have nothing in degree 2, which looks weird because you're supposed to have a z there. But actually, the thing in degree 2 is coming from the previous degree, degree 1. This has the homotopy type of a circle. And a circle, once you pass to its anima, that's bz. That's the same thing as bz. So it just shifts takes this and makes it it's pi 0 is 0, but its pi 1 is z. So that disappears in this degree, but pops up to a z in the next degree, and then so on here. This becomes 0 here, but contributes a z there, and so on and so forth. But then but how to recover the Archimedean information? So the solidification, it gets rid of i.e. the regulators. So these C's that you see here come from regulator maps. And you could just build them in by fiat. You can produce such a condensed spectrum by just gluing together Ku and something coming from the complex numbers. It's not too difficult to do, but we would like to see it arising naturally. And this is a big, I think a big open problem in our theory here is trying to answer the question of how to produce this K of C reasonable in some a priori manner, akin to how solidification produces little Ku. It tells you the Archimedean, the non-Archimedean information that's contained in the K theory of the complex numbers. Right, so that's a big open problem. And one possible solution is this liquidification that Peter's going to be talking about, but the result of that procedure is so mysterious to us that it's hard to know whether it's going to, yeah. We'd like to know what it does, but we have no idea. So it's hard to say whether that will provide a solution to this open problem. All right. And with the K theory of CP, you can do something though. Well, maybe I won't get into that so much. Maybe I won't get into that. Okay. So I think maybe that's enough talking about K theory. Before I move on to Marva E theory, are there any questions about that? I guess you would be typing them in the chat, maybe.
There was a question about the localization sequence from the K theory of Z to the K theory of the reals to the K theory of locally compact abelian groups.
Oh yeah, it should promote to a localization sequence of condensed spectra. But then again, we don't quite know how to make K of R reasonable except by building by hand the thing that is reasonable that it maps to. Like, so, yeah. Interpretation of regulators in condensed terms. I mean, you can build them however you like, you know, more or less classically, but do it in the condensed world. Like, you can build them in a lot of different ways using, for example, K theory, trace maps from K theory to Hochschild homology. Yeah, if you take well, what's the thing you can write down? So here's one description of regulators in condensed terms. It's not, I mean, I don't consider it very satisfactory. But you know, algebraic K theory always maps to negative cyclic homology. What's the notation for that?
HC minus.
Yeah, HC minus of C. But then if you go to topological K theory, that does you one better. It maps to the periodic cyclic homology of C. So there's this canonical map from the periodization map from negative cyclic homology to periodic cyclic homology. Right. So and this is the condensed thing. And if then this maps you K of C to this fiber product HC minus C, this derived this homotopy fiber product. And if you calculate the homotopy groups of this homotopy fiber, so here you only have C's I. And now let's take this cyclic homology over the complex numbers, say. So then here you have C in every negative or non-negative even degree, and here you have C in every even degree, whether positive or negative. So if you were to pass to the fiber term, then you'd only be getting C's in positive degrees, but with a degree shift, so it'd be in odd degrees. And then, yeah, so then if you take the algebraic K theory, this map is an equivalence with finite coefficients, but if you go with rational coefficients, it sort of behaves opposite. So the composite here is trivialized, and then you get an induced map from there to the fiber term, which has these C's in odd degrees, and that gives the regulators. Or you could just say, like, this thing here, if you look at what it is, you get exactly this thing here, and the regulators are kind of embedded in there. Or I feel like this is some X and mixed Hodge structures. I don't know. Yeah, so you could see this, I mean, in some sense, this picture kind of gives you regulators, and it works in the condensed world as well. And so that's fine. But what I'd really like is some a priori way to produce this thing from K of C as a condensed spectrum. That's what we don't have yet. You kind of have to know what to write down to get what you want. Right. Okay, so maybe I'll move on to Morava E theory. So this is a little bit of a test of this condensed framework. Nothing too deep is going to be going on here, but it's kind of this condensed framework is supposed to be good for mixing topological phenomena with homological algebra or more general homotopy theoretic phenomena. And Morava E theory is one place that where this kind of pops up. So what is the story here? So if you take you can take a perfect field of characteristic P, and then G, a height N formal group over K. So this is some kind of algebraic object over K.
One-dimensional one should maybe say.
What's that?
One-dimensional one should maybe.
Yeah, this is in homotopy theory, it's one-dimensional and commutative. I think that's automatic, but I'll say it anyway. Formal group over K. This is some kind of algebraic object over K that behaves like the formal completion of a one-dimensional algebraic group at the identity element. So you get some kind of group structure in a formal neighborhood of the identity element. If you choose a coordinate, it's encoded by a formal power series in two variables. So like fxy in K bracket xy, which satisfies the usual group law properties. So like fxy, fz, associativity, for example. That's if you choose a coordinate, but in general, we don't choose a coordinate. We regard it as some kind of abstract object. Anyway, there's a very interesting construction called Morava E theory, which moves this into homotopy theory, into the world of homotopy theory. And so this, I guess Morava, but then Gorse, Hopkins, Miller, so it really should be written E, K, comma, G, but it's actually often abbreviated to just EN, because for a lot of qualitative properties, it's only the height of the formal group that's important. I think I'm going to regret calling this G in just a second, but oh well. And what is it? So EN is a certain kind of E infinity ring spectrum. So that's the analog of commutative ring. In spectra. So in terms of the analogy between spectra and abelian groups, say, E infinity ring spectrum is the closest analog to a commutative ring. But it's an E infinity ring spectrum of a very special type, which makes it kind of amenable to an algebraic analysis. So it's even, so that means the odd degree homotopy groups are 0, and periodic. So there exists a periodicity generator in degree 2 such that the whole homotopy group ring is just the periodization of the pi 0. So all the even homotopy groups are the same. They're all isomorphic via multiplication by some periodicity operator. And then what is this pi 0? So this pi 0 is it's basically the only algebraic invariant you need to understand, because it's even in periodic. So it's just a commutative ring, and it is abstractly going to be isomorphic to the Witt vectors on your perfect field. So that's like adding a p-adic power series variable, but then you have to add some more power series variables. So x1 up to xn minus 1. So in total, you have sort of n formal parameters, where n is the height. So that's abstractly what it is. But what it's actually equal to is the yeah, the complete local ring parametrizing deformations of G. So there's this story with formal groups that if you have a formal group over a field, you can ask how does it deform. So if you replace K by K bracket epsilon mod epsilon squared, for example, you'd be asking about first order deformations, and you might wonder how many of those there are and so on. But more generally, you can grow your ring by adding more and more nilpotents and ask how the group is allowed to move when you slightly perturb the point. And saying that this complete local ring parametrizes deformations means that I should say I have a group law. I probably need to choose a coordinate here. Yeah. Wait, what am I saying? No, not plus coordinate. What am I saying? Well, anyway, yeah. What's that?
What you've written is correct, no?
Yeah. Right. Anyway, so the point is, if you have a formal group of height, right. So yeah. So the point is that deforming a formal group to a certain thickening of K, so some algebra which is a Artinian thickening of K, will be the same thing as giving a map from this complete local ring to K, commuting with the natural projection you have back down to K. So this parameterizes all the possibilities. Now this carries a universal deformed formal group. So G univ. So now this lives over this ring, but this is no longer of height n, of height exactly n. Rather, it actually has specialization. If you look at specializations to different points, you'll see arbitrary heights less than or equal to n. So the story is that a height n formal group can deform into a height n-1 or n-2 formal group, but it can't deform into a height n+1 formal group. So small perturbations of a height n formal group will produce a height n-1 formal group, and so on. So the simplest example of this is you can have the multiplicative formal group degenerating to the additive formal group. Although I guess that's height infinity, but maybe it doesn't quite fit into the picture. Yeah, but if you throw away some higher order terms in a height n group, you get a height n-1 group. Okay, so right, so that carries this formal group. And the other thing you need to know about this Marva E theory is that, so on the other hand, any even periodic ring spectrum carries a canonical formal group on pi naught. And this is an observation due to Quill, and I won't explain the details of how this works. And for Marva E theory, these agree. Okay. Okay, what is the significance of this? So we start with some algebraic data of a perfect field of characteristic P and a height n formal group over it. We produce this E infinity ring spectrum, which sees all heights less than or equal to n. Now, what is its significance in the land of pure homotopy theory? So there's this amazing there's this amazing correspondence between algebra and topology. So on the side of spectra, there is a series of approximations to the sphere spectrum. So yeah, I can map the sphere spectrum to the Ln local sphere, that maps to the Ln minus 1 local sphere, and so on. And the bottom term is the L0 local sphere, which is the Eilenberg-MacLane spectrum Q. So yeah, that's got pure rational information. And then it gets a little more complicated and complicated. And there is this chromatic convergence theorem due to Hopkins and Ravenel, or Hopkins. Oh gosh, I should have looked up the proper attributions for all these things before I started. Okay, yeah. By the way, Doug, are you there? I got an email from him earlier. No, I don't think he's here. Anyway, big shout out to Doug Ravenel for being a absolute brilliant mathematician who uncovered some of these amazing connections I'm talking about here and did a lot of great studies in stable homotopy theory. Right, so the sphere spectrum was actually recovered as the inverse limit of this tower. But on the other hand, these are supposed to be simpler to understand. So all the complication in the sphere spectrum is, at least in principle, contained in these LNSs. But on the other hand, these LNSs, these can be built in finitely many steps from your Morava E theory together with maybe its tensor product, smash product with itself, arbitrary number of times. But actually, you can stop at a finite step. So if you take Morava E theory and its tensor products with itself, then in principle, you can build a, no, it holds only after P complete? No, it holds on the nose. No, it's true on the nose, yeah? If you do it Kn locally, then you only need the first term, but if you include the other ones, yeah, no, this is a reflection of the fact that En covers the whole height less than or equal to n part. This is also Hopkins-Ravenel. It's part of the proof of the smash product theorem.
But still maybe only up to P completion. Because
what?
I mean,
what?
Everything you're doing is pretty much P complete on the right.
Oh no, P localization, yeah? P localization, yeah, sorry. Yeah, but not completion.
Yeah.
Mm-hmm. Sorry, yes, Gabe, I just misunderstood your comment. Sorry. Yeah, you're absolutely right. Yeah, just P localization, right? Right, and on the other hand, these things are accessible to study. Even these tensor products, part of this theory of even periodic ring spectra and associated formal groups is you can describe these tensor products also in terms of formal groups. So usually smash products can be kind of tricky to understand, but in this world, you can actually get a handle on them. So this is in principle, you're controlling something very complicated, which builds up the sphere spectrum in terms of these even periodic things, which look a lot more accessible to study. So the idea is that the stratification or the filtration of formal groups by height is reflected strongly in the innate structure of spectra. And this Morava E theory is a key thing that bridges this gap between the algebraic world and the spectrum world. So again, I guess this is this amazing idea of Ravenel, and it was verified a lot by Hopkins, Devenitz, Hopkins, Smith. There's a huge story in the homotopy theory related to this. Okay. Yeah, and this Morava E theory is the key, I would say, the key thing that connects the algebra to the topology. So it's a construction, and it's basically on deformation theory. But okay, why is this something that we might be interested in looking at from the perspective of condensed anima? Well, already I said that the pi0 of En is this formal power series ring. And this is naturally a topological object. So it's a complete topological ring. So we were considering En as a bare spectrum, which means a discrete spectrum, but on the other hand, it has this natural topological structure, and this would be, it's important to take this into account in a number of places, and I'll give some examples later. But maybe, okay, this was a little bit complicated. Maybe I'll take a little break from discussing this algebraic topology and introduce a let's do a toy version. So let me ask a very silly question. The question I want to answer right now is how to produce a natural condensed spectrum En. Yeah, sorry, maybe I'll ask the question. How to produce a condensed spectrum, condensed E infinity ring spectrum. I'll still just call it En, such that pi 0 of En should still be even periodic, of course, but pi 0 of En holds topologically as condensed abelian groups. So that the pi 0 is the inverse limit of the truncated versions of this with their discrete topology. So okay, that's the question we're going to be addressing. But let me now describe the toy version. This is going to look really silly, but there's a reason I'm going to do it. How to produce ZP as a condensed ring. Just the p-adic integers. Well, so there are many ways. So, but I'll give two answers. Well, one answer is, of course, you take ZP as a topological ring, and then apply the functor from topological spaces to condensed sets, and then it commutes with products or all limits, in fact, so it sends rings to rings, and then you're done. But let me give two different answers. So one would be, well, you can take ZP and always think of it as the inverse limit of Z mod P to the NZ, but now take these to be discrete, and then take this inverse limit in condensed rings. So these are discrete rings and therefore condensed rings. You could take the inverse limit in condensed rings, and then you're done because yeah, you just described a condensed ring ZP. Another way of saying this, which is maybe a little strange, is to just take ZP with the discrete topology, and then p-adically complete it, but in the condensed world. So in other words, this shows that you can build the condensed ZP just from the discrete ZP. You don't need to know anything else. You take discrete ZP, and then you p-adically complete in the condensed category. So you take the inverse limit over this discrete thing modulo p to the n, and you're just recovering this previous thing I wrote down here. So that's nice. But another thing you could do is maybe you want to describe what the value is on an extremely disconnected set. So you could set p-completing discrete Z will also work, Tomer, yes. But in case of Morava E theory, it's not so easy to produce an uncompleted version of Morava E theory. So we'll just have to take the discrete thing. Yep. Right. So another thing we could do is we could say that we take S to, well, we can take continuous functions from S to FP. This is an example of a perfect FP algebra. And then we can take the Witt vectors of that. So that is then that is the unique flat ZP algebra lifting continuous functions from S to FP. So you can build this by deformation theory starting from FP as well, or using this Witt vector functor if you like. Well, why are these options the same, by the way? Well, I guess you have a comparison map. Well, continuous functions from S to ZP, that is the inverse limit over n of continuous functions from S to Z mod P to the NZ. Well, this is a p-adically complete flat lift of continuous functions of FP. So it's a result of this deformation theory, the uniqueness of this Witt vector construction for perfect FP algebras that proves that it's the same. Okay, so likewise for Morava E theory, there are going to be two answers. And they both have their importance. So at first it looks like we're kind of out of luck in terms of the first option, because okay, we might be able to get the p-adic topology on the Witt vectors by p-completing Morava E theory, but what about these extra generators for this So the maximal ideal of this local ring has topological generators P and U1 up to UN minus 1. Where are the other ones going to come from? So, well, it turns out, so as for case 1, it turns out that for spectra, there's more than just P. You can intrinsically complete that. So in fact, there's a whole sequence. P, V1, V2, and it continues forever. So P is just usual P. So it lives in pi naught of the sphere spectrum, for example, which is the integers. And that's why, and since the sphere spectrum acts on any spectrum, you can have a multiplication by P map on any spectrum, just taking it like that. But this V1 is something that only exists once you mod out by P or some power of P. So this will live in some homotopy group, some even homotopy group. Yeah. Do I dare try to figure out something like this? Maybe I'm taking P odd here for P odd. In any case, in some high, well, no, not a homotopy group. Actually, I better say the right thing. It is an operator, a degree shifting operator. Yeah. From some suspension of the sphere mod P to the sphere mod P. So then it acts in a degree shifting way. On X mod P, or more generally X mod P to the N for any spectrum X. So it's a natural operation you have when you take so when you take X and you take X mod P to the N, there's an extra operation now, this V1, which you can complete at. And then for V2, again, it'll be a natural degree shifting operation for some other D on X mod P mod V1. So you can mod out by the V1 as well. Yeah. And then when you mod out by V2, you get a V3 and so on. And the upshot of this is that you can complete at any spectrum at, for example, P V1 up to Vn minus 1. And formally, it's a Gauss field localization. You can set it up as a Gauss field localization. Yeah, at sphere mod P V1 Vn minus 1. If you know what that means, or with respect to, I don't know, with respect to this spectrum. And then a nice thing happens with Morava E theory. So a priori, these VNs live in shift degrees, but they actually always live in even degrees. And I said Morava E theory was 2 periodic. So you can shift anything that lives in even degrees in Morava E theory, you can shift it down to 0, and then up to a periodicity generator to multiplying by a power of U. These VIs, these P V0, V1, Vn minus 1, you can put them into pi naught of En, and they generate, they cut out the ideal. Well, at least they're radical. How do I say that? There. What's the nice way to say that? They're radical is the maximal ideal.
They generate an open ideal.
Yeah, they generate an open ideal. Okay, thanks. So that completing at them is the same as completing at the maximal ideal. Right. Okay, so that's option 1. So we take Morava E theory as a discrete spectrum, which is built by the work of Hopkins, Gorse-Hopkins, Miller, and then we just take that thing and we complete it at PV1 up to Vn minus 1 in the condensed world. Or, I mean, we could have done it a little simpler, right? Because we can take En and view it as an En discrete module, and then complete with respect to those generators in pi naught we have. So, I mean, I didn't need to use that this was, that this operation makes sense for any spectrum. I could really just complete at P and then these generators U1 I had for the maximal ideal and so on, UN minus 1, because I can do everything in the world of En discrete modules in condensed spectra. So yeah, so that's just using generators.
And there was a question in the chat.
Yeah.
How is this still an E-infinity ring? And I think to see that in E-infinity ring, you might actually need to think about this working for any spectrum.
No, I mean, you can do it.
Localization description.
Yeah, I mean, the Bassfield localization description also works in this context here of En discrete modules in condensed spectra. So no, the reason it's an E-infinity ring is it's some general nonsense with Bassfield localization. Yeah, you can use either option. Right, so this Bassfield localization, for those who don't know, it's characterized by a universal property. So you have some spectrum you want to kill, say this S mod P V1 up to Vn, and then you can, well, what's the way to say it? So, well, you take your spectrum and then you put you build from colimits as many things that look like, well, the point is it gives a universal property for this P completion, which implies that it's lax symmetric monoidal. Yeah, so it sends E-infinity rings to E-infinity rings. Yeah, so you can either do the Bassfield localization in spectra to get the, with this P V1 up to Vn minus 1, or you can work in En delta modules and do the Bassfield localization just at the generators for the, or the completion, sorry, modeled by a Bassfield localization, just at the generators for the maximal ideal. But this first one is better because when we get to talking about the Ln local sphere, this is the one that's gonna, it's good to know that it's intrinsic. Yeah. Okay, so what about option 2? So this is going to be.
By the way, I mean, I think you missed the break.
Oh, I'm so sorry. Oh, did I go over time?
No, you're just not right there. No, it's a break.
Oh, okay. Phew. Yeah, I did go 3 minutes over though. I apologize for that.
No.
So yes. So okay, I'll stop for 15 minutes then. When should we meet back up?